remind you that, of course, I'm sure everybody remembers that next week is spring break. No one forgets that one. But the following week, I'm also going to be away. I'm going to be away next week and also the following week. And I'm leaving behind two not quite class-length videos on material and renormalization. One is a almost philosophical one. What's the thought process behind it? The other is a very technical one. So they're very different styles. We'll see how they work, and your goal is to come in with good questions when we get back to having a class the following Tuesday. And we'll review some of the material there and go to take the next step in renormalization. Okay, good. So today we have some fun stuff actually. It's a little bit of, it looks like a catch bag of a few different things, mainly connect to finding ground states and reading masses. But there's some interesting and non-trivial stuff that we get to cover today. So first, let's start with the trivial stuff. So let's just look at masses. Okay, I've set you up for this by a couple homework problems. But let's just, for the first one, take the case where we have a scalar field. And then there was some minus v of phi. And in case number one, it will take v of phi just to be m squared over 2 plus lambda phi over 4 phi to the fourth. So this is our typical phi to the fourth theory. The picture of v of phi versus phi then curves up, and it's pretty straightforward. And in this case, the mass of the particle is just m. It's just, you just read it off there. Pictorially, what you think about is you think about near the bottom here, the quadratic piece. Oh, sorry, I'm missing my phi squared. That makes more sense. The quadratic piece here, the shape of that curvature is the mass. Okay. So let's get a little less trivial. So this is case one. Case two, remember we did a couple cases where we changed the sign of the curvature piece, the mass term. Okay, and so the picture of this time now is v versus phi. V has a downward curvature to start with and comes back up eventually. Okay. Okay, and you all in your homework solved for the ground state. So this is the ground state. Occurred at what we've called v is the square root of mu squared over lambda. Okay. So that all this is the familiar stuff. Now the next question is, what's the mass of a particle in this case? Well, if you're thinking of a particle as an excitation from the lowest energy state, you actually don't expand around phi is equal to 0, but around phi is equal to v, because any excitation of phi around the lowest energy state is going to be out here, and it's going to be the curvature right there that plays the role. So let's just do that. Let's let phi as v plus phi twiddle. Okay, so in some sense we've just renamed phi. We could expand it around either vacuum, either ground state right there or there. But we're doing the same results in both cases. And then v of phi, and now we're going to look at phi total, is minus mu squared over 2 v plus phi twiddle plus lambda over 4 v plus phi twiddle to the fourth. Okay, well, there's a shift. There's a constant term. So if you just expand that, there's a term that looks like minus mu to the fourth over 4 lambda. It comes from two pieces. There's a negative piece from here and a positive piece from there. They combine to equal that. There's no linear piece because there's nothing. That's how you get the minimum. There's no linear term. Take the derivative to set it to 0. The next term it comes from two places. It comes from this phi squared with a negative sign, and it comes from the cross terms here where you have 2 phi twiddles and 2 v squareds. That adds up to mu squared. Okay, remember v squared is mu squared over lambda. So there's the lambda gets canceled with the v squared, you get mu squared. Mu squared, phi squared. There's a cubic piece, lambda v phi twiddle to the fourth, cubed, and then there's a lambda over 4 phi twiddle to the fourth. Okay, so our theory expanded around this state that has these terms, and the point to read out here is there's the mass term. The mass of this particle is positive again, so it's just like up there, it's positive. If you compare those two, you see that that's equivalent to saying mass is the square root of 2 mu. Okay, it's not mu, it's the square root of 2 mu, and it's positive. And we've been trying to read around that ground state. We've induced a new Feynman rule, a phi cubed rule. We have the old phi to the fourth rule. So now there's a new Feynman rule also. So this okay. So that's a bit of non-trivial stuff. Okay, questions about that? Okay, so part of the point I want to drive home is that reading the curvature at the bottom of the potential around the ground state gives you the masses, and the masses actually aren't what they look like in your original Lagrangian. Okay, so now it's up the ante, and I'm going to do symmetry breaking. And the Goldstone Theorem. Okay, this topic builds on the same thing, but except I'm going to make the game a little more complicated. I'm going to say that phi is now a complex scalar field, so it's going to be 1 over the square root of 2 phi 1 plus I phi 2. And v is going to be minus mu squared phi star phi plus lambda phi star phi squared. Okay, so we've now got two fields. They enter the symmetric combination. There's a symmetry associated with this, of course. Is phi goes to e to the I, let's call it minus I alpha phi. Okay, you change phi by a phase, the potentials invariant, the kinetic energy pieces are also invariant. Okay, so we've got a symmetry now. Okay, well, I've written the sign on that potential with a negative sign just like up above. And so again, if you think of this as a v versus phi, it goes down and comes back up, except that I've now got two phi's, and so I really should add an extra dimension there. So for one it's phi 1, and in the other direction I'll try drawing like this is phi 2. Then this picture, which is hard to then draw in 3D, at least for me, it's symmetric around that. It's, this is the typical Mexican hat or bottom of the wine bottle type of potential. It has a maximum there and minimum with a circular symmetry all around it. That circular symmetry is this phase because this phase rotates phi 1 into phi 2. Okay. So let's just plug ahead. There are lots of minimum now. There's a minimum right here, the minimum there. They're going all around. Again, they're all equivalent. If you choose any one of them, you'll get the same results. So I'll just choose the one that sits right here along the phi 1 direction. And so the minimum energy state is when phi is, it's actually, in this case, v over the square root of 2 is 1 over the square root of 2 mu squared over lambda. Okay. And the square root of 2 is just a normalization choice connected to things like that, root 2 in the definition. Okay. If I imagine expanding around that point, so now phi, this complex phi, is 1 over the square root of 2 v plus phi 1 twiddle plus phi 2. Okay, I've chosen it in the real direction so phi 2 doesn't change its definition, but just like we did above, I've taken phi 1 now and expanded it v plus phi 1 twiddle. So you can see that if I just set phi 2 is equal to 0, this is exactly the same problem we had before. And so I can write out all those terms without any more work. But then there's the phi 2 pieces also. Okay, so v of phi is minus mu squared over 2 v plus phi 1 twiddle squared plus phi 2 squared plus lambda over 4 v plus phi twiddle squared plus phi 2 squared quantity squared. Okay, and so there's a bunch of terms that you can write out that are like before. There's the minus mu squared over 4 lambda that comes from the constant piece at the bottom. There's a mu squared phi 1 twiddle squared. That's the mass term that we already talked about. There's a term, let me stick it way out here. It's lambda v phi 1 twiddle cubed. That's also a term that we had before. There's an obvious piece that's lambda over 4 phi 1 squared plus phi 2 squared quantity squared. That comes, phi 1 squared plus phi 2 squared. No, it's actually here. It's phi 1 squared plus phi 2 squared quantity squared is that guy. Those are the sort of less interesting pieces. There's one other piece here which I'll write down. It's not very interesting. It's lambda v phi 1 twiddle phi 2 squared. So there's yet another new Feynman rule. But the interesting piece, okay, is the term that multiplies phi 2 squared. Okay. Well, one of them comes out of here, It's minus mu squared over 2. Okay. And the other piece comes, so I just want phi 2 squared times the constant. So there's a v squared there, phi 2 squared. When I square that, there's a 2 v squared, phi 2 squared. So this becomes plus 2 lambda over 4 v squared. Okay. And the key point of doing this is that that's 0. Okay. V squared is mu squared over lambda, so these two guys cancel. Okay, so the end result of doing this is then the mass of phi 1 is 2 mu squared. The mass of 2 is 0. Okay, so we have a massless particle coming out of this thing. Okay, and you can get that from the picture. So let's just look at the picture temporarily, and this is the intuition that we're trying to build here. If I look at the state down here, I see that at this minimum, there's a curvature in this direction. So the curvature means the mass. Because if I excite the field, then I take some energy. So the curvature in phi 1 direction is non-zero. The curvature in the phi 2 direction is 0. So if I try making an excitation in the phi 2 direction, it doesn't cost me any energy. So I get the same energy all the way around. That's the intuitive explanation for what that is. This gets tied up into Goldstone's theorem. Okay. The features that we're seeing here is that the symmetry is hidden or broken. Okay. So the ground state. So we no longer have this phi goes to e to the minus I alpha phi symmetry. Actually, technically you do. I haven't done anything but just rename the fields. And so somehow buried in this mishmash of this Lagrangian here, there is some hidden symmetry that reflects the original symmetry. But it sure is pretty well hidden. You don't see it on the physical fields here. You have to sort of go back to this original field. So that's the symmetry breaking. The consequence of that is always, in a theory that has a symmetry, is that the ground state has many possibilities. That says continuous. Okay, so there's not just a discrete number, it's a continuous thing. And any given ground state breaks the symmetry. Okay. And then the consequence of that is Goldstone's theorem. Goldstone's theorem implies that there's a massless particle. Okay. So associated with the breaking of any continuous symmetry, there's a massless particle. And the logic is what the proof, the ultimate proof that you go into if you try to make it a mass proof, is just what we're saying intuitively, since excitations along the symmetry direction can't cost you any energy, there can't be any mass term associated with it. They have to be arbitrarily low energies if I excite along the direction of the symmetry. Yes. So if I'd made this an I and made it in the phi 2 direction, yes. So then phi 1 would have been the massless one. So the what I called 1 and 2 would have just interchanged in that case. And so it's basically, and the logic is then that then excitations in sort of the phi 1 direction this way don't cost any energy. Okay. Okay. So there's that extremely important. Any other questions on it? Okay, now I'm going to mess with it yet more. I'm going to talk about alternate names. Okay, so instead of doing what I did up above, let me try I'll call it, here's phi, 1 over the square root of 2, v, plus now I won't put a subscript on here rather than put too many names, e to the I chi of x over v. Okay, so I'm going to rename things. Instead of calling phi what I called it before, I'm going to choose this funny form. I've now got two fields. I've got that field and that field. And if I, look at this for small values of that field chi, it's 1 over the square root of 2, so I'm going to expand now. 1 plus phi twiddle plus I chi. The chi, I expand here. 1 plus I chi, the chi over v. The v cancels, I get I chi, and I get plus then higher order terms in that expansion. Okay? So it starts off looking, at small values of these fields, like this is like phi 1, that's like phi 2. But it's certainly not the same. These are very different. Okay? One of the funny features of this one is if I look at v of phi, so remember v was phi star, a function of phi star phi, that's minus mu squared over 2 v plus phi twiddle squared plus lambda over 4 v plus phi twiddle to the 4th. There's no chi in it at all. Okay, so that's the difference. If we go back up here and look at the potential had phi 2 squared all over the place. There's a phi 2 squared there, there's a phi 2 squared there. This one dropped out, but there are phi 2's in there. There are no chi's in this naming game. Okay? And if I look at the kinetic energy piece, the other piece which I haven't been writing, d mu phi star d mu phi, I don't know how much I should work on that. Let me it's not too terrible, but you can sort of see what happens. There's certainly two derivatives on phi twiddle. That's going to be down here. There's times when the two derivatives act on the chi. That will give you a piece which has this factor squared times derivatives of chi. I'll write that out. The cross terms cancel, and maybe you can just let me trust me on that. You can sort of see this is a real quantity. The cross term is going to have an I and a phi, so it's going to be imaginary, so cross terms end up canceling. Anyhow, this turns into 1/2 d mu phi twiddle squared plus 1/2 v plus phi twiddle over v quantity squared d mu chi squared. Okay, so the first term is the usual kinetic energy for anybody. This term also has the leading term at the v over v is the usual kinetic energy. But now there's also some interaction pieces there. Okay, so there's some interactions between phi twiddle and chi here. Okay, so here's our two seemingly different results. I'll write out the Lagrangians. L1 is 1/2 d mu phi 1 twiddle squared plus 1/2 d mu phi 2 squared minus m1 squared phi 1 squared minus lambda v phi 1 phi 1 squared plus phi 2 squared minus lambda over 4 phi 1 squared plus phi 2 squared. Okay, so that was the potential from above and the various things you see. There's this guy's massive. There was the that should be a twiddle there. I can't write on the screen, but there we go. There's this cubic interactions, which I pointed out, and there's the quartic ones, which I also pointed out. In the second case, I chose different names, and it starts off looking somewhat the same. D mu phi twiddle squared. There's then a plus 1/2 1 plus phi twiddle over v squared d mu chi on d squared minus m1 squared phi twiddle squared. And then the other pieces are pretty similar. It's minus lambda v phi, there's no phi, it's not phi 1, it's phi twiddle cubed minus lambda over 4 phi twiddle to the 4th. Okay, so the interactions of phi 1 and phi twiddle are exactly the same. Okay, but the oddball pieces here are that by changing the names, I've generated a whole new different set of interactions. So I used to have these two pieces here as my interaction terms. Now there's none of that. The only thing that's sitting here is this phi over v. Okay, and so let's do some practice exercise. Let's come out with some Feynman rules. Okay, and I'm interested in the following process. I'm interested in the interactions of this either phi 2 or chi. Those are the ones. They're somewhat the same. You know, they're both massless. There's no mass term for chi here, so it's also massless. But otherwise, the interactions are different. So let's do a couple of them here. There's the ones that are relevant here. I can write out an interaction with phi 2, phi 2, phi 2, phi 2. Okay, that's just that's the lambda over 4 phi 2 to the 4th. So that's just minus 6i lambda. And there's also an interaction that it's relevant for what we're doing is phi 2, phi 2, phi 1. Okay. And I read that out of here. So there's a phi 2 squared phi 1 that turns into minus 2 I lambda v. So the coupling constant is lambda v. There's a factor of 2 from the combinatorics of how you apply phi 2. Okay. On the other hand, if I try writing out similar rules in the other case, let's try chi, 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 chi. Well, there isn't any term like that. That's 0. There is a term that looks like chi, chi, phi. Okay, it comes from expanding this guy. So here's a chi, there's another chi, there's a phi at the linear piece there. Okay, if this is, now it's momentum dependent because it's derivative, so this is P1, P2. Actually, let me make it P3. That makes my notes look better for what I'm about to do. And this is minus 2I over V P1 dot P3. Okay, the derivatives, the 2 is again this combinatoric factor. There's 2 combinatoric, there's one, the linear term here has a 2 phi total over V. I cancel that one half. There's another factor, combinatoric factor from the using the 2 phi's, 2 chi fields here, one in the initial state, one in the final. There's a counting factor there. That's the 2. And then the P1 dot P2 is the derivatives. Okay, everyone see those guys? Okay, so this is a little disturbing at this stage. We started with the same theory. You may have chosen one set of names, I chose another set of names, and we end up with a different set of Feynman rules. And they're way different. Here's the scattering amplitude, and here's 0. Okay? And the amazing thing is that these are actually exactly the same theory for every amplitude you ever calculate. It sure doesn't look it, but I'm going to do a calculation to show you. And so the amazing thing is that names don't matter. Okay, and this is called Haag's theorem. And those are 2 A's there, H-A-A-G theorem. All physical results are the same. Okay, and that deserves an exclamation point. Okay, and you have to see this a few times to believe that it's going to work out, because it sure doesn't look like it's going to work out here. I'll do one calculation so you can see how it occurs in that case, and then we'll accept it from then on. This is actually not very much discussed in field theory books. I actually don't know if it's in Peskin and Schroeder anywhere, but it's used all the time. People take advantage of this all the time. There's often a lot of times when you can, by choosing the names cleverly, make your life much, much easier. And in fact, this example, you'll see the chi names are much easier than the phi names. And we're going to do the simplest calculation. It becomes even easier for complicated calculations. Okay? So to do this calculation, I have a little prelude, which is on kinematics. And you should also pay attention to this, because these are the variables that I'm going to use in the subsequent things, in particular in the renormalization example. I'm not going to redefine them. So I'm going to define, here we've started to see these already. S is P1 plus P2. This is the Mandelstam variables once again. so we're doing some process with P1, P2, P3, P4, and something happens in between. Two guys in, two guys out. Okay? That is the center of mass, center of momentum, energy squared. That's not what that guy is. Okay? And then the other two variables are T is P1 minus P3 squared. That's most often people call that Q squared. Yeah, Q is a variable that you can use for a lot of things, but that's often called Q squared. And U is P1 minus P4 squared. And these are all the variables you need. Okay. I'm going to use an important property of this. And so let me do this now. We're going to apply this for these massless particles. So for massless particles, okay, we have S is, well, it's P1 squared plus P2 squared plus 2P1 dot P2. Remember, P squared is M squared for the particles on shell. So this is 0 plus 0 plus 2P1 dot P2. T is minus 2 P1 dot P3 by the same type of calculation. U is minus 2 P1 dot P4. Again, the P squares all cancel. And so we end up with S plus T plus U. It's 2 P1 dotted into P2 minus P3 minus P4. By conservation of momentum, P2 minus P3 minus P4 is P1. So it's minus P1 actually. So it's minus 2 P1 dot P1, which is 0. Okay, so the sum of ST and U is 0 in this case. In general, S plus T plus U equals 4M squared. Okay, so if I didn't set the mass equal to 0 and just carried along all these masses, you get mass squared, mass squared, mass squared, mass squared, mass squared, mass squared, minus 2 mass squared equals 4M mass squared. Okay, that's how a calculation would go. And so these vertices that I just wrote out there, if I write a chi, phi vertex, that was IT over V. Okay, and if I write another one, this one, P1, P2, phi, so annihilating into phi, that's then minus IS over V. Okay. This is for the chi's here. Chi. Okay. Okay. So that's just kinematics. But now let's do the calculation. If there's no questions, let's do the calculation. Let's calculate phi 2 plus phi 2 goes to phi 2 plus phi 2. Okay, so scattering of these guys. All right, well, the obvious thing that you do is, well, here's pictures. Pictures, there's that vertex. Okay. That's obvious. That's what we normally would write. So we'd write minus 6I lambda for that. But I'm actually going to say there's a couple others coming along too. Let's go back up here and look at this. There's a phi 2, phi 2, phi 1 vertex, and so I could exchange a phi 1, scatter phi 2, phi 2, phi 1, phi 1, phi 2, phi 2. Okay? So there's another diagram which I could write as this guy. So now I'm going to label these things P1, P2, P3, P4. Okay, so that one's easy to write out too. The top vertex is minus 2I lambda V. The propagator is I over, it's P1 minus P3 squared, so it's T minus M squared, and then minus 2I lambda V. Okay. And, well, there's another diagram. There's one that goes like this. P1, P2 propagating into a phi, so that's phi across there. Phi 1, actually. P3, P4. Okay, that's, it's again 2I minus 2I lambda V. Each of those vertices, and the propagator here involves P1 plus P2, which is S, so it's S minus M squared. And then there's one last diagram, which you would write like this, where P1 scatters into P4, and we do the exchange here again. P3 comes off of P2. So that's a distinct one. And the only thing different about it from the first one is that the momentum flowing down here is P1 minus P4. That's a 4. So this is so it's plus minus 2I lambda V squared I over U minus M squared. So you get STs and U's in that symmetric form. Okay. Well, that looks like a mess, but I'm going to play with it. Let me do the following. I'm going to write everything, factor out as minus 2I lambda V. Actually, no, I'm factoring out just 2I lambda, sorry. 2I lambda. Okay, and so I've got a factor of 3 for my first term, and I'm going to write 3 in a very fancy way. 3 is going to be S minus M squared over S minus M squared plus T minus M squared over T minus M squared plus U minus M squared over U minus M squared. Okay, that's a fancy way to write 3. And then the next terms then all come from these propagators, and clearly I'm doing it because I've got these 3 propagators here. And all these propagators, I factored a 2I lambda, so I'm left with a lambda V squared there. It's actually 2 lambda V squared, so it's 2 lambda V squared. And the propagators are 1 over S minus M squared plus 1 over T minus M squared plus 1 over U minus M squared. Okay. At this stage, you have to remember that V squared is mu squared over M squared over is mu squared over lambda. So this is 2 mu squared, which is, when we go back to look at it, it's the mass of particle number phi 1. So it's 2m squared. So it's what we mean by m squared. M is the mass of particle. And at this stage, you see that there's going to be a lot of cancellations going on. I've sort of led you into this. There's m squared over s minus m squared, and the s minus m squared over s minus m squared. So the m squareds cancel. Likewise, the next one, the t's and the u's. Okay. So m squareds cancel, and we're left with minus 2I lambda. Okay. S over s minus m squared plus t over t minus m squared plus u over u minus m squared. Okay? But I'm not done. Okay? Now I'm going to write 0 in a fancy way. My fancy way of writing 0 is s plus t plus u over m squared. Okay? S plus t plus u is 0. So doing that. And now by doing that, you see that at very low s, when s is small compared to m squared, when s is very small, this is going to, you drop that one compared to m squared, s over m squared with a minus sign cancels this, t over that cancels that. So there's an extra cancellation going on now with small m squared. So in fact, this thing actually grows like s squared, not just like s. So if you combine these up, here I've got s. You gotta combine these two pieces by putting, common denominator and all. Okay, I do that calculation. This turns into minus 2I lambda over m squared, s squared over s minus m squared, plus t squared over t minus m squared, plus u squared over u minus m squared. Okay? That stage I'm done. Actually, I have one little thing that makes my next thing easy. It's no more of these adding zeros and ones, but I can write this term as minus I over v squared, because remember, so m squared is 2 mu squared, and mu squared is lambda v squared. Okay, so after all that work, we get to there. Okay, now the easier calculation, let's now consider chi plus chi goes to chi plus chi. So remember, these are the massless particles in the other name. Okay, well, again, we can do minus Im is that plus this guy plus this guy there. So, 1, 3, 2, 4, 1, 4, 3, 2. Okay, so again, everything's the same except I'm exchanging these. But now I have a different set of Feynman rules. Our Feynman rules for that guy were 0. And here's where the fun comes. If we go back up here, we see that our Feynman rule for the exchange diagram is T over V. Okay. So I get this guy is minus I, well, let's see, let's do it right, plus I T over V times I over T minus M squared times I T over V. And likewise, the next ones come similarly. It's minus I, it's actually I F over V quantity squared, I over S minus M squared, and likewise the last one is U's. Okay, and so now we end up with I over V squared, S squared over S minus M squared, plus T squared over T minus M squared, plus U squared over U minus M squared. Okay. So this way, very trivially, we get that answer, whereas we had to work up above. So it's the same result. Okay, it's certainly much easier in this second representation. You just bang, 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 you're there. The first one requires these cancellations, and you might not have even recognized that the cancellations were there until you started trying to work. And it gets much worse if you try, more complicated diagrams. This is as simple as it gets. So the second representation is better, and that's why this is used a lot, is if you can make such a renaming that makes your work easy, theorists always love to do it. Okay, so Haag's theorem applies to this. And Haag is a very mathematical physicist, or was. I don't know if he's still alive. And the real proof is very fancy. The physics proof, though, is pretty much the way I always think of it is, if you look at those two Lagrangians, you start off with particles with the same mass, and they started from the same Lagrangian, of course, but the phi's and chi's have the same masses in the two cases. So I'm an experimenter, and I take one of these particles. I only see the free fields. I send them into an experimental region. Something comes out. That something coming out shouldn't depend on whether the theorist chose to use phi names or chi names to do it. Okay, the experiment shouldn't make a difference. Individual Feynman rules could, because the rules change it as you rename, but amplitude shouldn't change, and so they don't. It's not any two names. There has to be, so any chi, which is some function of my original fields. Okay, so let's imagine I have a whole bunch of original fields phi's, and I rename them into these chi's through some nonlinear transformation, any nonlinear transformation. Okay, the only thing that has to be the same is that at leading order, Fij of 0 is delta ij. Okay, so this piece tells us the kinetic energy pieces are unchanged. So yeah, you can't make it work. Well, it may somehow work, but you can't make it work in a trivial case where you've done names that don't make sense. Here, the naming that we did, let's go back way up here to it. I showed you that phi 1 and phi 2 and phi, twiddle, and chi are the same to first order, and all the nonlinear pieces are higher orders. So this satisfied the Haag's theorem, so the kinetic energy pieces ended up being unchanged. And that's the only condition. All right, so let's get down here. Okay, so that's the only condition that you have to apply. That's pretty amazing to see it happen in practice. Okay. Comfortable with that? If you're comfortable with that, we're going to up the ante a little bit more. I'm now going to do the Higgs mechanism right. Again, I've set you up for this by the homework problem. The Higgs mechanism uses this fact to explain how the mechanism works. So we did this case here. We took scalar electrodynamics with complex scalar field, just like the one we just had, minus v of phi star phi, and this is going to be the same as above. Okay, it's going to be that piece. This has not only a symmetry, the phase symmetry, it has a gauge symmetry, which was phi goes to phi prime with e to the minus I. Well, no, let's make it a lambda. I tend to use lambda here. Lambda of x. And if I put a charge in front of there, q lambda of x, makes the next formula nicer. And a mu goes to a mu prime is a mu plus d mu lambda. Okay. So a gauge change on the photon and a space-time dependent phase change on the scalar particle. Okay, so now, just like you did in the homework, we do this spontaneous symmetry breaking, which is the mechanism I just outlined. The ground state can be chosen to be v over the square root of 2. And as you worked out in the homework, the piece that looks like d mu phi star d mu phi equals lots of stuff, but then picks up a q squared v squared over 2 a mu from the piece where phi goes like the square root of v. And this gives a mass of the mass to the photon is GV, QV. Okay, so that part you worked out, and that part's unchanged. Okay. There is a puzzle here, though. Okay, we started out. It's a classic puzzle here. We started out with a massless photon and two phis, phi 1, phi 2. Okay, so two fields. And if we just count how many types of states there are here, we know in massless photons there's two polarizations, so we'll call it 2 degrees of freedom. And the two scalars are 2 more degrees of freedom. there's four things that you quantize here. You know, you've got two polarizations and two scalars. And we seem to have at the end, we seem to have a massive photon. And phi 1, phi 2. So we've suddenly got three polarization states and two scalars. And that adds up to 5, where we put a question mark. Okay. So somehow we seem to have gotten extra states, extra degrees of freedom. You know, we used to have, for every momentum, there was two photon polarizations, one and two scalars. Now I've got three photon polarizations and two scalars. Okay. What? Well, a massive spin 1 state has three polarizations. Okay, spin up, spin 0, and spin minus 1. You know, this is the MZ values. Okay, good. Thanks. Anybody else question that argument? Okay. Well, and if you just try writing out this Lagrangian using one set of names, you in fact seem to see that. However, we're now going to choose a different set of names. We're going to use this other set. Phi is 1 over the square root of 2 v plus phi twiddle e to the I chi over v. Okay. And well, how much do I want to do here? Let me do the following. Let's take a look at the d mu chi piece. Okay. D mu phi. So the kinetic energy piece. That's where the action is. Okay. When I take the derivative on that, I have derivatives on phi. I've got the a mu piece in there, and I've got the derivatives on chi. Okay. So I'll take a look at those guys. So there's the first piece is the d mu phi twiddle. That's an important piece. And I'm going to pull out e to the I chi over v over 2 out, square root of 2 out in front. So there's one piece, clearly. There's the piece, the derivatives can act on chi, and so that piece has v plus phi twiddle times d mu chi over v. And then there's the gauge piece, which is IQ a mu v plus phi twiddle, and the e to the I chi just passes. It sits there. You know, there's no derivative, so it's there also. Okay. Okay. So the Lagrangian that I write out now has, that's minus a quarter f mu nu plus, well, the kinetic energy pieces are 1/2 d mu phi twiddle squared. Then there's a set of terms that look like it's, I'll write it as q squared over 2 v plus phi twiddle And here I'm going to do the following. It's A mu plus d mu chi over qv quantity squared. Okay, so I've combined, I've taken the v plus phi, right, it's q a plus d mu chi over v. So I'm combining those two pieces there together. And I've missed the factor of I here. I know, no one caught me, but remember I'm taking the derivative here, there was an I there. So the I's actually work out properly. Should be an I right there. Okay, again, the cross terms cancel. These guys are imaginary. This guy is real. Cross terms drop out. So that's actually the piece. And then I have the v of phi piece, which is plus mu squared over 2. Well, it's v plus phi twiddle squared minus lambda v plus phi twiddle squared. Okay. So actually, some of this you can easily see. If I had just forgotten about the photon, I just dropped the photon out. It's exactly our problem before. It was the scalar. This is the scalar piece, and I had the kinetic energy piece, this potential energy piece, and the v plus chi, that's a squared, excuse me, and times d mu chi squared. Okay, so if again, I need that correction there. So if I've forgotten about the A piece, it's exactly what we had the step above, but now I have the A piece there. Okay. Well, now we see the next of the odd and interesting features that we have today. I can do a gauge change on A. I'm going to let A prime is A mu plus d mu chi over qv chi of x. I do the gauge change. That's A prime now. F squared is unchanged. The point that gets the exclamation point now is chi has disappeared. Okay. There ain't no more chi in the whole Lagrangian. There's nothing out here. There's nothing there. F's unchanged. This is the photon field. So I end up with one less particle than I thought of. So I really only have the massive photon, and I have one scalar. Okay. So only one, and so in fact I do only have 4 degrees of freedom. This last one was completely spurious. So if I'd gone through it and used the phi 1, phi 2 notation, I would have had all these terms here with phi 1 with phi 2s in them. And I would have done lots of calculations and find that every time I calculate something, I get 0 as the amplitude. By using this name, it's obvious that this field just doesn't exist. It isn't there. So the phrasing of this, the Higgs mechanism, is that the longitudinal spin 0 part, longitudinal gauge boson It comes from the Goldstone. Remember, chi was the Goldstone boson, the massless degree of freedom. And it's disappeared from this theory now, and it's been replaced by the longitudinal. It's a massive state, but it's a spin 0 state of a spin 1 particle. It's really, really odd. Okay, but that's what happens. You saw it in front of your eyes. Okay, the phi twiddle there is this. Phi twiddle is the residual Higgs boson. Residual. Okay. So in the standard model, this mechanism is used. It's used other times too, but in the standard model, there's a bigger symmetry. There's a SU2 symmetry. Which is broken, spontaneously broken. That would normally imply 3 Goldstone bosons. And those become the longitudinal states of the W plus, the W minus, and Z0. And the leftover guy, I mean, I'm not working this out in detail for you here, but leftover guy is the Higgs boson that's going to be found in the next couple of years. Okay. Okay. All right, good. I reached exactly where I wanted to reach. We're at a transition point. What we've done a lot of stuff. We've made the transition from quantum mechanics to quantum field theory. So you guys have that. We have the quanta. We have the Feynman rules, the transitions, the matrix elements, the cross sections. Technically, the last thing that we need to do to complete this is tell you how to deal with loops. And guess what's next? That's what we do. We tell you how to deal with loops. When you start doing loop diagrams, you end up in